I was, and now I'm not anymore.
Got it. All right, so we'll try and get started on time. So first of all, there's a couple of announcements from Louis. So the seminar committee is looking for members. And at the moment, I think there's a gap in the oceans and climate side and the geophysics side. So if anybody from either of those areas would like to volunteer for the seminar committee, please see Louis or email Louis or have a beer with Louis or do whatever you want with Louis. It's being filmed. Okay, so now on to today's speaker. So it's a pleasure for me to introduce Nicolas Flament. He's currently a senior lecturer at the University of Wollongong, where he has been since 2016. So Nicolas got his PhD on the Coherent scheme, so linked with ENS in Lyon and the University of Sydney with the Earthbite group. And he graduated there in 2010. And then, as I said, moved to Wollongong to be a senior lecturer in 2016. So after a few years as a postdoc, he investigates the deformation of Earth's mantle and its expression at the surface over long time scales, so tens of millions of years to hundreds of millions of years. And I think we'll see today potentially to 1 billion years. So very long time scales. And he does this by combining global geodynamical models with geological, geophysical, and geochemical observations from lots of different data sets. Amongst other things, Nico is widely considered a global expert in combining plate motion reconstructions with these mantle dynamics models and going further and further back in time to understand the evolution of the solid Earth and its diverse expressions at the surface. So including things like dynamic topography and sea level change. Now, those of you that have met Nico today or had pizza with him will realize he's an awesome human being, but not only is he an awesome human being, he's also a wonderful and highly awarded scientist. I won't go through all of the awards he's won, but I'm going to read some of them out. So he received a DECRA, which he based at University of Sydney. Yeah. In 2017, he was awarded the Outstanding Young Scientist Award from the EGU. He won the David Syme Research Prize in 2021. And most recently, he received the Anton Hales Medal from the Australian Academy of Sciences, which is in honor of Anton Hales, the founding director of RSES. So Nicolas received that award for work at the interface between geodynamics and geology through novel 4D mathematical modeling of flow in Earth's deep interior. So look, we're obviously very excited to have you here. It's been a long time since we had many seminars in person, so we're delighted that you can join us. Thank you. I think the turnout in the room speaks volumes for how excited the school is. So over to you.
Thank you. Thanks very much, Audrey, for the introduction. Thank you all for your very warm welcome. It's very exciting actually to be seeing scientists again face to face. Vern, thank you so much for organizing the visit. It's terrific. I'm really enjoying it so far. So this work is sponsored by industry. It stems out of a linkage proposal. The industry partner is De Beers. So with the Australian Research Council, this is 4 early and mid-career researchers getting together. Omar Bodo is a postdoctoral fellow at UOW. Simon is a future fellow at UTAS, starting soon at UTAS. And Andrew is a Marie Curie fellow at Leeds in the UK. So this is about setting the lower mantle free. The title of the paper is Assembly of the Basal Mantle Structure Beneath Africa, I think. And there's been a lot of inspiration and work. This work builds onto work from several people in this room. So thank you. You'll recognize yourselves. This is borrowed from one of Audrey's papers. It's looking at seismic tomography in the deep earth, where we have blobs. I'm going to call them blobs. You may know them as LSVPs. LSVPs are seismologic structures. In the mantle flow models, I have temperature anomalies, so that's why I call them blobs. Otherwise, I would call them in the paper, I call them basal mantle structures. We've got a blob under Africa, a blob under the Pacific. We know them well at long wavelength, and more detail appears over time about these two. So here's a view of them in 3D, and they are slow in S waves. And here's a view in 2D, and many of you, and we've looked together today at some of these figures. Here's the blob under Africa, and here's the blob under the Pacific Ocean, about 200 kilometers above the core mantle boundary. About 15 years ago, the first paper I think about this by Burke and others in EPSL was in 2008. There was an insight which is important, which is that the largest volcanoes, so the type that wiped out the dinosaurs, if you think of the Deccan traps at 65 million years ago, there's only a few of them. There's about 25 of them in this particular picture. When they are reconstructed to their place, to their location of eruption with a tectonic reconstruction, it seems they line up with the edge, or they line up with the blobs, and some argued with the edge of the blobs. So this can make sense because it's been thought for some time that these volcanoes come from that might be linked to very deep mantle plumes. There's few of them, and so the relationship was extended to also include kimberlites, which are these black dots here. There's many more kimberlites than there are of these large igneous provinces. The problem with the kimberlites is that it's unclear how the kimberlites are linked to flow in the deep earth. The mechanism is not clear. The second problem with kimberlites is that some of them in North America don't really fit with the blob model. And this would be linked to subduction instead. So this model here was used to say there's a relationship between the blobs and volcanism at the surface. And you can see there's many more volcanoes in the African region than there are in the Pacific region. There's no kimberlites in the Pacific region because the oceanic floor has been destroyed and tends to carry less kimberlites in the first place anyway. The correlation works for the last 320 million years, which gave the idea that perhaps the blobs could be used as a fixed reference for tectonic plates carrying volcanic products. This is appealing because in the Earth, everything moves. And before 200 million years ago, there are very few constraints available for tectonic reconstructions. Paleomagnetic data are very useful to constrain latitude, but for tectonic reconstructions, there's no constraints for longitude. And so the idea here was to say, if the latitude of a block is known from paleomagnetic data and the block carries a volcanic product, if one accepts that the blobs have been fixed for a time, the tectonic block could be reconstructed to the margin of the blob at the time the volcano was erupted. So here are two examples, one in Siberia and Australia at 355 million years ago. So the latitude of the Siberian block is unknown, the longitude, sorry, and it's assumed to be here on the edge of the African blob. And then another example for the African plate at 500 million years ago, 505. This is significant because in tectonic reconstructions, the African plate is at the top of the tree and everything falls under it. There are two major assumptions here, that the blobs have been fixed and rigid through time. The third one is that it's the edge of the blob that matters as well. And this was a problem, or this is a problem, because our current understanding of geodynamics, of global geodynamics, is that the blobs are pushed sideways by subducting lithosphere deep into the Earth's mantle. There's two processes at play here. The slabs sink and push the mantle in front of them. And the second one is the advection itself on the slab. The core material gets down. It also needs to create real estate. This figure here is from Alan McNamara. At the bottom, we have this cross-sectional cartoon view, and at the top again, we have another set of hotspots shown to correlate with the blobs as imaged by present-day tomography. Now, everything in the Earth moves. We think hotspots moves, but more importantly, we think subduction zones move. For the last 200 million years, this is not too much a problem, because so the two outlines at the back here, the vote maps from leakage and others, another way to look at the position of the blobs. This was from 5 tomographic models. The outside contour is where at least one model gives a blob, and the inside solid contour is where 5 models agree there's a blob. Okay. That's one way to map the blobs. And what you can see here with the subduction zones on top that are colored by age, you can see that for the last 200 million years, which is essentially post-Pangea, they are away from the blobs. And up until a few years back, we only had tectonic reconstructions extending back to 200 million years. When the Sydney group and others started, and the Oslo group started extending the reconstructions further back in time, what we found, and these are reconstructions, so they are uncertain, what we find is that the location of subduction zones crosses over these blobs. So if you accept the previous slide, without doing all the work I've done, you expect that the blobs move. Okay. Now I'm going to do the work to show that actually it makes sense that the blobs move in models that are driven from the top. These kind of models, they use sitcom S. So Louis wrote sitcom, Chizong made it sitcom S. This is the spherical version. And then Dan Bauer and Mike Giannis modified it to assimilate tectonic reconstruction from the Sydney group. And as I mentioned, when I first started playing with these models too long ago to disclose, we could go back to 230 million years ago, and now we go back to 1 billion years ago. And we're working on going back a bit deeper in time. Obviously, as we go further back in time, there's more and more uncertainty. Okay, but we can also eliminate processes that might be of interest. And this image at the bottom is by Sabine Zahidovic, who's at Sydney Uni. I think he's a DECRA fellow at the moment. So it's to illustrate what goes into the model. On the left, at the surface, we have the tectonic reconstructions with the age of the ocean floor. We have the tectonic velocities at the surface. Inside the Earth here, what is shown is slabs going down, and they are colored by depth. So it's an iso temperature contour. And the lighter the color, the shallower the slab in this case. Again, this research benefits from infrastructure that is on the ANU campus. So they run on, this was run on GADI. Each simulation is about 150,000 computer hours. The initial condition of the models is that 1 billion years ago, we insert slabs. We insert them to a given depth. In this case, I chose 1,000 kilometers. And you can see that they are an angle in the upper mantle then to a depth of 420 or so kilometers, I think, and then straight down. And they are thickened a bit in the lower mantle where the viscosity is greater. Here's the same picture shown in 3D to give you an idea where the slabs are. There's 2 more things I need to mention. So that we've got an adiabatic gradient of temperature. So temperature increases in the Earth. These are extended business models for the modelers in the room. And at the base, I also have a chemically distinct layer that is either denser or not than ambient mantle. Okay. And the last key you need is that we've got continent at the surface, and these continents also have a chemically distinct material that is lighter than ambient. So an important aspect of these models, they're driven from the top. And so the subduction history we impose at the surface is quite important. Time here on this slide is a bit funny. We start at the bottom right, go up, come back down, and go up. So we have subduction zones, age-colored at around about 100 million year intervals, I think. And you can see that further back in time, they cross over the present-day position of the blobs. So that's the case to 500 million years ago, and then 250, and then in the last 200 million years ago, or 250 again, the relationship is different. I'll come back to this and show another view of this for specific snapshots later. One important point is the reference frame, and we are here in the no-net rotation reference frame, and I'll come back to this as well a bit later. Almost being terrific in producing very nice animation of the interior of the Earth. What we're looking at here is in 1 million year increments. The evolution of the model for the last 300 million years. We're looking at the African hemisphere. What you have at the surface in green are the plate boundaries. In white is the outline of continents. You can probably make Africa out now as you follow the cursor, and Madagascar is here. Inside the Earth, again, we have the cold slabs sinking, colored by depth, and they are darker when they are deeper. And then we have what I'm calling the blobs today. And these blobs, they're colored by, it's an isotemperature contour again, colored by depth, and darker is shallower. You can see that new subduction zones appear, and I'm going to comment now on what happens in the last 300 million years. The African blob is not one blob at 300 million years ago in this model. You can see that there's several smaller patches that move, and they are, in between them, there are slabs that must have sunk to the bottom of the mantle earlier. And now there's slabs from the northern Tethys and from the western Gondwana that are going to push the blob together. And when we get to the last 60 million years or so, we get a coherent African blob. I'll come back to this a bit later. This is the crux of the story.
Can a slab become a blob?
That's an excellent question, Richard. I'll take it at the end. Is that okay?
Yeah.
I'm not sure. Gordon would like it to. I don't see this in these models. Now, the prediction at present day in temperature from the mantle flow model looks like this. So this is at 200 kilometers above the core mantle boundary. And now we're looking at non-dimensional temperature anomalies. So the blobs are red, they're hotter than ambient, and away from the blobs, we've got slabs that are colder than ambient. So I kind of have a problem here. I want to compare this to that, which is the map of S40 RSES at the same depth. There's neat ways to do this, and I'm working on this with Audrey and Sia and Omar at the moment. And these guys have done more work in that space. What I've done to do this, I've used, inspired by the work by Lekic and others, I've used cluster analysis. Essentially, a set of points is thrown at the surface of the Earth and split into a number of clusters, here too, according to a property with depth. The depth range is between 1,000 kilometers that we chose, 1,000 kilometers to 2,800 kilometers, again following Lekic. And in this case, for tomographic anomaly, it's the VS that is the property that's mapped. The algorithm minimizes the distance for each point to the mean of one of the two clusters. And what we get here is that we have a slow anomaly cluster and a fast anomaly cluster. The slow anomaly cluster is the blob, and the fast anomaly cluster is away from the blob. We do the same for the mantle flow model. The anomaly that's mapped this time is temperature, and we get a hot blob and a cold blob. The hot blob is here in gray, and the cold blob is there in white. One key I forgot, which is important for this comparison, is that the area of gray covers 34% of the Earth's surface in S40 RSES, and it covers 34%, it turns out, for this particular flow model as well. The next thing I can do, and I've played this game before, is to work out a match between the two maps. So this is what that looks like. One can use several indicators. I'm using the indicators that give the greatest value, which is the accuracy. In orange is true positive. It means the flow model's done a good job of putting the blob where it should be. In gray is the true negative, which is no blob, as predicted as constrained by the tomography, divided by the total area. There's two more, which are the false positive. Essentially, we have a blob in the flow model, but not in tomography. And then the false negative, where the tomography says there should be a blob, but the flow model doesn't find it. I use the accuracy. If one uses the sensitivity, the scores are much lower, but the trends in the models are similar. So here I get a score of 72%, which is not too bad, and it's driven up by the very large area of gray. Now, this was a time-dependent, sorry, this was a present-day constraint, and what we wanted to do, or what I wanted to have, was a time-dependent constraint. And so this is inspired by the work of Thorsvik and others. I used two databases for volcanic products. I used the Tapper et al. Database for kimberlites, which are shown here as small circle colored by H, discs colored by H. And go figure, I put the volcanoes at diamonds, the diamonds are in the kimberlites. I was inspired on that day. These are the large igneous provinces from Johansson and others. One thing to say about these, they have the plume heads, but also the plume tails. So the Hawaii, Emperor Bend, all of these chain would be in there, okay? Which is adds compared to the plume heads only. These are reconstructed at the age of eruption and shown with S40RTS in the background here. What I did for the analysis, I combined them as one database of volcanic products. This is their distribution through time. And you can see this is for the last 320 million years. What I've done, I'm looking at my flow models in 20 million year increments. So I've binned the data to be in 20 million year increments. You can see there's a peak in the kimberlites at 100 million years ago, and another peak here at about 140 million years ago. The lips, we have a fair bit for the last 150 million years, and then not so many. So now it's pretty cool. What we can do, we can look at what Thorsvik and others told us to look at, but look at it in a time-dependent way. And Rodri had done that before as well, but in a not in a truly time-dependent way, I believe. And that's what that looks like. On the left-hand side, you have the flow model, so things move. On the right-hand side, you have the tomographic model, so this is the Thorsvik world, and things don't move. The volcanoes do move at the surface. And what your eye wants to do here is to try and track the distance of each of these symbols to the blobs. And what I did for each of the points, I measured the distance using pi-g plates. I measured the distance between the volcano and the closest blob. And I worked out empirical distribution functions. What you can see from this animation is that it seems to be around about the same distances for the moving and the fixed blobs. And then when we put them together, it turns out to be the case for these two models. So on the left-hand side, I have the flow model, and on the right-hand side, I have the tomographic model. What I'm reporting here is the median. So this is the cumulative probability in an empirical density function. And this is the distance. The distance is signed because in this case, I'm considering the case in which inside the blob is different to outside the blob. So distances are positive inside the blob on the right-hand side and negative outside the blob on the left-hand side. Okay. The average distance in the flow model is -1 degree, so slightly outside. And in this particular tomographic model, it's -4.2 degrees, so a bit more outside. The next thing was to do statistics with this, inspired by both Rodri and Mark, and that took me a long time because I'm not as smart as them. I eventually got there. What I did for each of the flow models I considered was to take random points that we'll see here as red squares. And I have 931 of them, which is the addition of the other two databases. And I'm using the same temporal distribution, which is important for this test to know. And now we can look at the points as earlier and the random points as well. And then it goes to chickenpox at some times, which is a bit weird because you don't see that in the distribution of the volcanic products. This is because kimberlites tend to occur next to one another. So the kimberlites come in clusters, and this plays in the favor of the sample as opposed to the random case. The random case will be scattered all over, and the kimberlites are clustered on continents that are close to the African blob. Okay. And so what I did, I just showed you one iteration, but for each tomographic or mantle flow model, I did 1,000 iterations, which are shown in gray here. And then I used a statistical analysis to differentiate, to check whether the blue empirical distribution function was different to the gray random, each gray random empirical distribution function. I used two metrics. I checked first in a mean sense. So I checked that the mean of the absolute values of the distances was smaller in the blue than in the gray for each comparison. And the second one is a Kolmogorov-Smirnov test, essentially checking that the blue is in a statistical sense, the blue distribution is statistically significantly different from each of the gray distributions. I reported that as a fraction. So if the fraction is 1, it means all 1,000 tests are passed. And here in this case, we have 0.97, which means 30 tests didn't pass, but the other 970 did pass. Okay, and then it gets gory because I used many models. So I've introduced 4 metrics to you. The first one was the area covered by the blobs. The second one was that accuracy for present day. The third one was the median distance. And the fourth one was that statistical test. This plot has 3 rows. And I was devastated to format my Python, to hard code values in my Python script so that the print version of the paper is incorrect. So this is the corrected version where the x-axis labels are correct. At the top, we have 7 tomographic models that I use as my target. So the gray ranges in the background are from the 7 tomographic models. Then we have a first series of flow models, and then we have a second series of flow models. In the first series of flow models, I varied the viscosity of that basal layer. And in the second series, I varied the density of that basal layer. So the viscosity, I found a sweet spot in terms of accuracy and distance around 10. So then I ran with that. So that's what I selected for my viscosity. And then I varied, not systematically, but almost in 0.5 also increments the density. So what we found is that there was a sweet spot around here for accuracy, but that model C6 had a fractional area that was less than for the blobs, so smaller blobs. And so in the end, my preferred model was C7, which has slightly lower accuracy, but this fits in terms of the, and that's the one I've been showing in terms of the area. For the distances, you see that the density plays a role on the distance. And when you have very large density, you end up with larger blobs. And so the volcanic products reconstruct within the blobs. Okay. Note that I didn't find one model that is in the gray range for all of them. And I left it at that because I didn't want to fine tune any more than I had to. There's already been a bit of turning these buttons. I'm not going to do all the sensitivity tests here. They're in the paper and I'm happy to entertain all the ones I've done at least. The main one, or one of the main ones, is the tectonic reconstruction. I did mention earlier that on the right-hand side is the no net rotation that I'm using here. On the left-hand side is the original reference frame with the tectonic reconstruction I'm using. The key point to see here is that when we go to no net rotation, the volcanic products are pushed away from the blobs. So for the present day comparison or for the Torsvik comparison, it's actually not favorable. I'll explain why it's important for the flow models in a minute. Just the sensitivity test here. At the top, we have the tomographic models again, but for the original tectonic reconstruction, if you will, with the paleomagnetic reference frame. Here we have the no net rotation, and what you can see is that the distances have been pushed out. Importantly, previously, and I'll go back to that because that was key, I forgot to mention that statistically, the flow models perform as well as the tomographic models. Okay, so they pass the test, and that's the key for the paper, or a key for the paper. And now at the bottom, I have 2 mental flow models. One is based on the original reference frame and the other one on the no net rotation. So for stats and distances, they are not, you can't distinguish them. The original one that's better for the fractional area in this case, but it wasn't fine-tuned. I fine-tuned that later. But what you can see is that for the accuracy, the original reference frame performs poorly. And that is why, if I go back to this is the first case at 0.72, which is a happy story. And this is what it looks like if I have net rotation at the surface. This looks like a dog's breakfast, so the blobs are not in the right position. And this has been known for some time. So this is work by Rudolph and Jean. Essentially, their work was a bit different because they removed net rotation within the mantle. I removed it at the surface, but the effect is the same. When there is net rotation, the basal structures get shifted in longitude, which is ironic because this is what they want to be used for. And this is why for the mantle convection model, it's important to use no net rotation. I'm going to do two more things, and hopefully I've not put everyone to sleep. Maybe I should have taken your question earlier, Richard. I'm going to talk first about supercontinents. So upstairs, downstairs, there's been that idea, and this is a very cool paper from 2007. These are steady state or transient model, I should say, rather, and not truly time dependent. On the left-hand side, it's an Earth without continents. And it's a 1 degree Earth in the sense that it has one giant downwelling and one giant upwelling. And what this shows is that if there's a girdle of subduction around a supercontinent, then we go to degree 2 Earth, with still one giant blob away, but under the supercontinent, away from the girdle of subduction, there's also a second blob, a second upwelling. These models now, again by Zhong and Rudolph, are similar to the ones I just presented, generally. One difference is that they didn't go as far back in time, okay? They went to about 400 million years back in time, I think. And what they suggested was that the African blob could have been mobile before 200 million years ago, but less so after 200 million years ago. So it was kind of a happy medium where the Torsvik world would work for the last 200 million years, but perhaps not before. And what I'm going to argue is that this is because the reconstructions didn't go as far back in time as the ones we're using, bearing in mind the uncertainty of going further back in time. So what we found with the scenario we used was that around the West Gondwana block at 740 million years ago, there's a network of subduction zones. You could say it's busy there. Okay, I think Alan Collins he knows that area quite well, and his input is in that model. The other thing I'm going to highlight in the following are two subduction zones in the last 400 million years, one offshore the Americas and one to the northern end of the Paleotitis Ocean. And this is what we found. Essentially, these slabs coming down from the west, around the West Gondwana blob, are now trapped. They started at 740 million years ago. We're looking at them now at 500 million years ago, and they've been piled up at the core mantle boundary, just above the core mantle boundary. And so the blob is away from them. And this slab in the model persists because it's a very big slab. It diffuses slowly, and it's still there at 80 million years ago. And then slabs from the northern Tethys and the western Gondwana margin push the different parts of the African LSVP together and warm up this raft of cold material in the middle. I'm going to show you an animation in 20 million year increments. And this shows that the blob, the African blob, could have assembled in the last 100 million years. It's a bit jumpy because it's in 20 million years increments. What you see is that West Gondwana, I'll try and follow them the second time around, sorry. And then if you train your eye in again on the African blob, it comes together really in the last 100 million years in this case. So I'll try and follow the West Gondwana slab that's here. It goes down, it's there. And then it's, follow my cursor, it's still there. Moves a fair bit, so there's potentially still too much net rotation in these models. And then eventually it's going to be trapped in there and warmed up. I'll just do once more the one in 100 million year increment and 1 million year increment for the last 200 million years, because it's much smoother. And you can see these rafts of cold material being heated up because warmer material is pushed onto them essentially. So the point here is that we find, and we saw that for quite a few models, that it's possible that the African blob was not one blob, but several blobs in the last 100 million years, which is quite a difference from the previous model suggesting at least 200 million years. And finally, I'm sticking my neck out a bit here, and that's an aside, but there's also a geochemical implication. So the Duperl anomaly or that kind of thing was thought to be hemispherical in a north-south sense. This is work from 1984, suggesting that in this area of this, in the south hemisphere, we have positive 208 to 204 lead anomalies, and away from that, they're negative. Recently, the Curtin group, so this is work led by Doucet, proposed that this hemispheric pattern could exist but be related to the blobs, the African blob and the Pacific blob. Their results depends on plume selection, I should highlight. But this is how their story goes. We're again looking at 208, 204, against this time 206, 204 lead as opposed to 207 earlier. And you can see that in the Pacific, the northern hemisphere reference line is rather followed by the data follows that line quite well, but not so much in the African hemisphere. And the argument that Luke and others put forward is that this could be explained if upper continental crust had sunk to the African blob, essentially. I told you earlier that in our models, we have continents that are chemically distinct, and this was with the idea to maintain them at the surface of Earth, but there's a bit of leakage, if you want, there's a bit of entrainment from subduction zones. And what we did, we mapped where these continental crusts would end up in the model. On the left-hand side, we have the African hemisphere. On the right-hand side, the Pacific hemisphere, and you can see a lot more material has sunk into the African hemisphere, simply because continents have been on top of this for longer. So I'll show you an animation of that. And you'll see that there'll be more snow on the left than on the right. And so this suggests, at least for the last cycle, so let's call it the last 200 million years or so, this idea put forward by Doucet and others could work from a dynamics perspective. With this, I'll conclude. I'll say that all this work to turn a must into a may. So the history of volcanism is as compatible with moving blobs as it is with fixed blobs. The blobs may be moving over time, and that is consistent with our current understanding of global geodynamics. The blobs could come together and break apart, a bit like continents at the surface. So maybe we have super blobs and blobs, although as more data become available, it seems there's a bit more structure to the blobs than just a degree 2 structure. The African blob may have come together in the last 100 million years, rather than having been fixed and assembled for 550 million years or more. And finally, the African deep mantle domain could be enriched by the subduction of continental material. Thank you for your attention. I look forward to your questions.
Thank you, Nico. Very interesting talk with, I think, a lot of material there for almost everybody in the room. So let's open it up to questions. Whilst everybody's thinking, maybe we'll start with Richard's and go from there. So Richard, ask your question again.
Yes, I don't think you responded, but I think the answer would be, I'll push you again, would be yes.
So your question was again, are the blob...
Can a blob become, sorry, can a slab become a blob?
Can a slab become a blob? Well, it depends.
I suppose you qualify that saying, well, maybe the part of the slab may be pushed out of the way of the blob. Sorry, part of the slab.
But what we see here in these models, I'm not tracking the chemistry of the slabs, so maybe I should do that.
Yeah, well.
And Max Baumer's done that in Cartesian models. And Mimingly and others have done that too, I think. And what they find is that blobs might acquire some slab material over time.
Yeah.
I don't know if anyone has actually shown a dynamic model where a blob is made up of slab. I know the idea is out there. I don't know, and then chemically it could work. Dynamically, I don't know if it's been shown to work, that the entire blob is made up of slab. What we see is that the slabs tend to push away something else. So the other idea here is that the blobs could be primordial, could be from the freezing of the magma ocean. It could be the rafts at the base there. And they might have been forever in that sense, but moved about. My models don't speak to that. I just should stress that my initial condition is a bit naive, and it's slightly more consistent with the primordial model, although it's at 1 billion years, and there's 3.5 billion years of history before that. So Max Baumer has a model in which part of it, the base of the blob, will be primordial, and the top is a bit of a layered cake. So I don't know, Richard. The two ideas are out there. I don't think the idea of slab to blob has been shown to work dynamically, but I might be wrong, Roger.
There's some recent work by Tim Jones, who used to be here, who he argues that I think the blobs would be a mixture of primitive materials, and that'll be supplemented by subduction. But again, I think it's still very much open to debate.
Yeah, you could extend this by thinking when you think some of it is made up of a primordial segregation from the magma ocean, where that needn't necessarily be a complete chemically conserved piece of mantle. That something has changed. If you fractionate a magma ocean and end up with parts of it that you accumulate someplace and parts of the rest accumulate none.
That's right.
But that's different from a Phanerozoic slab, which is taking really the upper mantle and melting it one more time, but ending up with a very small chemically different layer, the oceanic crust, underlain by a depleted mantle, taking that crust out of it. And then the rest is the same old upper mantle. But that could look different. That slab ought to look different compared with something that you took out of the magma ocean.
Yes.
Where you put, it's Blinky's law, with some of it plus the rest of it's all of it.
Yes.
And I'm suggesting that Blinky's law applies differently to the products of a magma ocean compared with a Phanerozoic plate, a lithosphere plate construction.
And the question would be, how do we tell them apart?
Yes.
And so models are one thing, but I think ultimately this will come out of seismologic work, I think.
Might be pretty subtle.
Yes.
After all, the seismologists generally have a hard time distinguishing various flavors of matter.
The other thing to remember is for these models that are so long, the slab's thermal signature will diffuse over time, so a lot of the negative buoyancy will go away.
That's hard compared with chemicals, isn't it?
Yeah, but what's taking them down mainly is their thermal negative buoyancy. When that goes away, I guess the chemistry, whilst it's still a little bit important, it's largely a passive aspect of the mind.
Yeah.
So I think there's time scales and stuff that come into that question, but that's
question. Just sort of about the fact that, I mean, nothing in the moves vertically. Right? It's always curious about how the reconstructions of the surface and the reconstructions of the base tie to one another through a path that is not straight up and down. It should be somehow. It's not linear. It depends on the flow model.
Yeah.
So how does that either get taken into account by uncertainty?
Okay, so I'll try and repeat and tell me if I'm not doing this correctly for Zoom. So Louis' observation is that the link between the surface and the bottom or the deep earth is not vertical and there's lateral motion. And the question is, how does that come about, essentially?
Well, how do you take into account when you try to make the connection between the edges?
Yeah. And how is that lateral motion taken into account? Yeah, well, you hit it on the head. Essentially, that lateral motion comes from, so we've removed the net rotation, which is the degree 1 component of that, but then from the plate velocity and the lateral viscosity variations, which are not very large in these models, we still get a lot of lateral motion in these models. I actually think there's too much lateral motion in these models. And if you look at the Titis slab, you can see that that's one of the slabs where we, and this was blatant, and I'm not hiding it away. I still think there's some of the better models out there. But the Tethys slab here, we've got a problem with the African LSB is not matched well, and that's. I think this comes from the convergence rate at that particular subduction zone. So I'm working on this with an honor student at the moment to try and look at what drives the behavior of slabs. So in a nutshell, Louis, I think it's a known unknown. There is some lateral motion, possibly. I think in these models, there's too much lateral motion of slabs, and as a consequence of the rest. The observation is at the present day, still we get something that's in the right spot somehow. Starting from a shot in the dark at 1 billion years ago, but it's very much driven by the last 200 million years of history.
Have you done any tests about your initial condition? In the sense that, well, I agree it's quite complicated to reconstruct a billion years ago, there comes with uncertainties, but how would the final picture get changed if you were to shift things by 200 kilometers?
So the question is, have I tested different initial conditions or the sensitivity of the model to the initial conditions? So this type of model is known to be very sensitive to the initial condition. I varied the slab depth initially. That's got a small effect. It has an effect, but a small effect. I've changed the initial age, and this has a more important effect. I've carried out models with a spin-up phase where I imposed the same tectonic reconstruction for 250 million years, which is at least the time it would take for slabs to sink all the way to the bottom. So it shapes the basal layer. And then I start at 1 billion years and let it go. And that has a significant effect as well. So that's it. You've got details of that in the paper. And in there, what I talked about most was the initial age. But yes, they are known to be very dependent on the initial condition.
Any other questions? I have one question. So when you showed your, I think it was the 200 million year animation, some of the plumes seem to be very long-lived. Have you looked at the lifetime of the plume in your model relative to what we expect on Earth? I realize we can't, there's an upper bound that we can't get because of the plumes. Are they long-lived?
So the plume tails are long-lived in here. The plume heads, we don't see them most of the time. Actually, in this animation, you'll see them. When I look in 20 million years, I missed most of them. No, that's a very good question. I've done that with Melissa in Stag-Wai models, and I'm looking at this now. I've done a pilot project on shorter lived models that actually never went to the. So what I did, I characterized the lifespan of plumes in there, but I didn't compare. I think what you mean is on Earth is the. Okay, let me spin this around. The Hawaiian emperor.
How old is it?
How old is it? Do you know? Because I don't know. Do you know?
It's more than 90 million.
Sure, it's
So
more than
give or
90
take,
million,
probably
and then
put it to 200, probably you would say.
right, and then same with the Iceland plume. How old is it? It might be 200 million years old.
60.
The plume is 60, but then can't you link it to that?
Camp?
Yeah. No, not the camp. Sorry, the Arctic magnetic province.
Yes.
Some people have proposed that, and then the Hawaii one. Some people have proposed that this funny flavored subducted rocks at 180, or I forget, somewhere offshore on the East Asian coastline. I think that would be at 180 a potential link to Hawaii.
The Navy kites you're talking about? Navy kites?
That might be. You're the petrologist.
The 200 million probably pretty safe.
I think so.
As an initial guess.
But if you look at the oldest plume track on Earth, the Galapagos, which is 130, I realize they've been subducted, but it's quite an interesting test. I don't know what the answer is.
Yes, but the point is some of the tracks may be older because so the Hawaiian emperor, you lose it. Yeah. And then people have proposed, and I think again for the Iceland one, it's been proposed it might be up to 200 million. I think.
I don't know. Any other questions? Oh, see it? Hey, so did I understand right that you implied that the African blob might have a different history compared to the Pacific blob?
Yeah.
Because it might happen like in different time. So my issue with the degree 1, degree 2 story is it should have a big effect on the rotation of the Earth. We don't see that in fact. So I might suggest the Pacific might be also different blobs. We just don't have data for that.
There's a lot there from Sia. For Zoom, I'm going to try and repeat. The question is, can we have a degree 1 Earth that would affect the rotation of the Earth with respect to the core, so that should be seen in the true polar wonder? It's not to be seen. And so the Pacific blob should probably be more than 1 blob at times. So I agree on all accounts, and I'll just flag as well that in the reconstruction, the Pacific hemisphere is quite naive, even for the last 200 million years. The paper for me, or there's 2 papers at least that come to mind from the Oslo group and affiliated researchers. There's a Vandermeer and others in 2012 in Nature Geoscience that makes a case for intra-oceanic subduction in Pentalassa in the last 200 million years. And then there's a Dolmeyer and others in 2017 in Science Advances, I think, that makes the case for back-arc basins in the northern Pacific Ocean in the last 80 million years, I think. This is not captured well in the Sydney reconstructions. So that's one aspect that with a better, with a more realistic subduction history in the Pacific hemisphere, there would be more than 1 blob. As for the true polar wonder part, I agree in general, I think, and I would just add to this that what we found in our models is that because there's continents, as long as you have continents, it's very difficult to have a degree 1 Earth. And if one agrees that there have been continents for 2 billion years or more, or perhaps 3 billion years or more, then the question is, when did tectonic plates start? But it's unlikely to have a degree 1.
Any more? No? Okay, on that note, I think we'll thank Nico once again. Before we do that, from correct if I'm wrong here, I think there are beers downstairs right away. And then the plan is to go to Benscope for more beers and food from 6:30. So everybody's welcome. Thank you again, Nico.
Thank you.